So welcome to Lecture 5 of the Vehicle Dynamics section of Automotive Technology. This is all a bit of a new experience for everyone presenting online, but let's give it a go. If you've got any questions, just let me know either by raising your hand or typing something in the chat box. I shall try and monitor that as well as we're going along. That is what the other person in the moderators is me actually twice. So yeah, give us a if you've got any questions, let us know. Like I said, you can click the raise your hand at the bottom of the screen if you've got a question. You want me to stop and answer the question, that's fine as well. And if you've got any problems hearing me or whatever, just let me know. I assume that everybody can hear me successfully, so let's make a start. So last week we covered low speed cornering in lecture 4, and this week we're going to move that on to high speed. So it's a bit more complicated with high speed because our tyres now are no longer simple devices with no slip angles. We've got to involve slip angles. So in terms of an outline, we'll talk about cornering at high speed, what that means, how it works. Talk about steer angles and slip angles, okay, and then talk about the couple of critical speeds and characteristic speeds that we need to discuss as well, about how to work those things out. So high-speed cornering, what does that mean? Well, at low speed, as we discussed last week, tyres travel in the direction they're pointing. Okay, so the slip angles are 0, and tyres, like I said, just simply travel in the direction they're pointing, which is all fine and good. But as you increase the speed, the tyres start traveling in the direction they're not pointing, and that difference between those angles is called the slip angle. Okay, so the lateral acceleration is at a much higher level. Okay, and to counteract this acceleration, the tyres need to generate the lateral forces. And the way the tyres generate lateral forces, as we discussed back in lecture 3, is that they generate lateral forces through slip angles. Okay. So, as we said with slip angle, that's the angle between the direction the tyre is pointing and where it's actually travelling. We covered this a couple of weeks ago. Okay, and assuming you've got linear tyres, and we'll talk about non-linear tyres possibly later on. But assuming you've got linear tyres, then the lateral force you can generate with the tyre is a function of the slip angle, and the constant there is called C alpha, and that's known as the cornering stiffness. Okay, we covered that last week, and so the lateral force is Fy. Okay, and then the cornering stiffness is a constant that's a function of the tyre and various characteristics about the tyre. And alpha is the slip angle. Okay, so there's a typical tyre characteristic. Okay, and you can see that as you increase the slip angle, you reach a peak with the tyre in terms of the lateral force being generated. But if you look at just low slip angles, so in this particular case up to about 2.5 to 4, 2.5 to 3, the characteristic is more or less linear. And what we're doing in this module up to this point is we're going to assume that tyres are linear. Okay. In fact, if you cover if you choose to do motorsport performance next year, next academic year, we'll actually discuss how you deal with the non-linearities of tyres. But at the moment, we're just going to deal with the linear stuff. So up to, in this case, like I said, I've put it at about 2.2 or something. But yeah, it's a linear tyre characteristic. So we assume this is a straight line, and that no matter what the slip angle is, your coefficient, your cornering coefficient, will be, sorry, the cornering stiffness will be the same, irrespective of where you are on this graph. For a given load, so for different loads, obviously there'll be different curves, and the C alpha will be different depending on the load, but we'll cover that in a minute. So, in fact, let's do it here. So, lateral force is defined as zero camber angle. Okay, a positive step angle produces a negative force. Okay, so in terms of sign conventions, if you've got an angle that's positive, which I believe is to the right, the force is a negative, which means it's to the left. But the SAE defines the cornering stiffness as the negative of the slope, such that it takes a positive value. So, like I said, there's a bunch of different things. Sometimes you'll see cornering stiffness actually defined as a negative value, but obviously, the way we've drawn it here, that's clearly a positive value. So, but like I said, it depends on how it's been defined. And the cornering stiffness, as we discussed, depends on tyre size, tyres type, number of plies, chord angles, wheel width, and tread. For a given tyre, the load and inflation pressure are the main variables, and that's how you can tell the difference if you drive your car and it's got a low tyre pressures. You can feel the difference in the way the vehicle is handling, because inflation pressure has a big factor, is a big aspect of the stiffness of the tyres. And clearly, if you have low inflation pressure, the tyre is less stiff, giving you less ability to grip in the corners. If you imagine your C alpha has gone down, if you look here, if your C alpha is down here, then obviously for a given slip angle, you're generating less lateral force. So that's how you can tell the difference. Now, the cornering coefficient is a different sort of constant, and that's the cornering stiffness per unit load. Okay, so this is the way to get out of having different loads. Is you can come up with a factor that's got a stiffness per unit load. It's the largest light loads and reaches the rated value at the limiting load. So C alpha is divided by the load Fz. So that's the way to calculate the cornering coefficient. Okay, so it's cornering coefficient C alpha, and that's C alpha divided by the vertical load. Now I have here got a in-class question, but one of the issues I've got is we can't discuss the solutions on Collaborate. So it's up to you really how we do this. What I have done is I've produced videos of the solutions that will be uploaded after this lecture. So if you're happy to go through that after the session, and then we can do that. Are you happy with that? Anybody? Okay, so yeah, it's replied. I assume everybody else is happy with that plan. Okay, I think that's probably the easiest thing. There are a couple of questions right at the lecture as well, and they're a bit more involved. So we'll go through there. Like I said, I will have videos of those solutions that will be available after the lecture. But this is a very straightforward question, just to get based upon that equation. This one here, you just go through and calculate the cornering stiffnesses for those things. So the stiffness divided by the load will give you the answers to these questions. But like I said, questions 2 and 3 at the end of the lecture are a bit more involved. So we'll go through the videos for those. Okay, so the equation. So assuming a vehicle has a constant, has a forward velocity v and is going around a corner of constant radius, the lateral acceleration, centripetal acceleration, is given by v squared upon r. Okay, you may have seen that back in level 1 dynamics. Okay, and that's known as the lateral acceleration. It's a function of the forward velocity and the radius of the corner. Okay, and clearly, if you double the forward velocity, your lateral acceleration will go up by 4 because it's a squared term there. Okay, that's our lateral acceleration. And if you if you multiply an acceleration by mass, you get a force. Okay, and so for the vehicle of mass m to successfully negotiate the corner, the lateral force generated by the tyres must match this. So you've got lateral acceleration, or lateral force, sorry, Fy, and that can be split across the front tyres, Fyf, and the back tyres, Fyr. Okay, and that must equal mass times acceleration. Those are the sum of the forces, mass times acceleration, and we know that Ay is v squared upon r. Okay, so you'll see this Fy, which is the lateral force generated by the tyres, must equal the lateral force, mv squared upon r. Okay, so that's the first equation. This lecture does get a bit equation-y in terms of the numbers of equations in here, but it's all, hopefully, my explanations should help explain and provide you with some clarity. So that's quite straightforward. The Fy is the forces generated by the tyres, okay, in the lateral direction, that's what the y means, okay, and that's going to be the mass times the acceleration in the y direction, which is v squared upon r. Okay, so clearly, like I said, if you double the speed, the lateral force goes up as well by a factor of 4. Okay, lateral force at the front axle, lateral force at the rear axle, and those are the things. Now, When you're dealing with cars, we often assume that the radius of the corner is a lot bigger than the wheelbase of the car, and you actually model your forward vehicle as what's known as a bicycle model. Okay, so there's our forward vehicle with our inner and outer steer angles, our wheelbase, okay, and our track width. Okay, and what you can do is say that's equivalent to one wheel at the front and one wheel at the back, and those angles, the delta is the average steer angle. You've got your radius going to the centre of gravity, and notice that we've got these are the thick arrows is the direction the wheels are travelling. Okay, so this one's got travelling this direction, the back wheel's travelling this direction. Okay, and obviously you've got slip angles here, so that's alpha r is the rear slip angle, alpha f is the front slip angle, and the forces being generated are perpendicular to the direction the wheel is travelling. Okay, they're not perpendicular to the tyre, it's actually which way it's going. So they're perpendicular. So we've got FYF being generated at the front, FYR being generated at the rear, and notice that because we've got this slip angle at the back and at the front, the centre of the corner is now no longer in line with the rear axle. Okay, if you remember last week when we looked at it, we had the tyre travelling in the direction that it was pointing. Okay, so the centre of the corner will be in a line projected by the rear axle. Okay, but now because we're generating slip angles at the front and the rear, okay, the center of the corner is now not in line with the rear axle. Okay, you've got C and D, add them together, you get your wheelbase. Okay, and like I said, you've got FYF and FYF and FYR being the forces being generated. Okay, so that's known as the bicycle model, and we'll refer to this model a couple of times, but this is the way we work this stuff out. And remember that these tyres in the bicycle model are representing two tyres. Okay, so you'll see some twos pop up in the equations when they may not, and that's because when you're working out the stiffnesses, often the data will be for one tyre, and you need to multiply that by 2 to get the actual the force being generated. So we'll cover that in a minute. Anyway, so there's the bicycle model. Okay, and if we take moments about the centre of gravity, we can do some various things. Again, assuming small angles, okay, but so obviously this distance, this obviously isn't perpendicular to the bigger direction, but it's close enough. So moments about the centre of gravity, positive being clockwise, we've got FYF times by distance c. Okay, that's trying to rotate the vehicle in a clockwise direction, minus FYR times by distance d. So that's this one going in this direction. Okay, going anti-clockwise. And so obviously that must equal 0 unless because the the vehicle otherwise will just be spinning around on the spot. Okay, and so you can rearrange this equation to solve for this one. FYF is a function of FYR. Okay, so they're related depending upon those distances in the wheelbase. So you can see. And if we substitute this into the equation for a lateral acceleration, okay, so we've got an FYF here, okay, and we pop that term in for FYF, that equals mv squared upon r, and obviously if you take this term and you put it into this term, okay, you're going to get FYR, which is this FYR, times by d upon c, FYF, plus 1, which is this term here. Okay, and that must equal mv squared upon r. And you can go through, if we said 1 is c upon c, okay, then you can add them together, you get c plus d over c, which is FYR, and obviously c plus d equals L. Okay, so you can see the lateral acceleration, okay, mv squared upon r is a function, you could actually say it's just FYR, okay, times L upon c, and obviously in FYR we know is c upon L times by mv squared upon r. So again, like I said, just by rearranging this equation here for this term, okay, so this equals this. If you want to solve for FYR on its own, then the c comes here on top, the L goes here on the bottom, we end up with c upon L, okay, mv squared upon r. And likewise, you can go through the same motion for FYF, and you get mv squared upon r times d upon L, okay. So although you're working out the front lateral force here, notice that this is d upon L, which is this, is the rear picture here. Okay, that's because obviously if you've got more mass on the front, okay, this point here is going to go towards the front. Okay, and more mass on the front means that it's the D upon L, which is bigger than C upon L. Okay, which is the way that works. Okay, so front is D upon L mv squared upon R, and back is C upon L mv squared upon R because of where the weight distribution lies. So analysis, shouldn't the force vector be 90 degrees with the distance? So I'm assuming you're talking about these forces here. Is that correct? 90 degrees. Yeah. Well, the reason why that, like I said, we're assuming these angles over here they're exaggerated on the drawing. Okay, and we're assuming small angles, so we can make the assumption that this is going to be more or less perpendicular with C, and this one's going to be more or less perpendicular with D, which is why they're slightly out of which is why it's slightly different from what you would have thought. But yeah, that's a fair point. And clearly, if we were doing nonlinear stuff, we'd include trigonometric terms, which would give those values perhaps more accurately. But this is sufficient for what we're doing. Okay, so if we go through, so there's our FYF and FYR that we found just on the previous slide. Are we all following so far? No problems? I assume everything's okay. Like I said, feel free to comment with the microphone if you want to. It's up to you. Whether you choose to do that. Right. Okay. So let's continue on. Okay. So FYF and FYR, and we know that the front mass is M D upon L. The rear mass is MC upon L. Okay. So again, distributing the front and rear. We can actually, you can see we've got MD upon L here and M upon L here. So we can actually replace those things with MF and MR. Okay. And we also know that, so this is where that 2 comes in, and we know the lateral force generated at the front and the rear axle is dependent on the front slip angle and the Corning coefficient. But like I said, with the bicycle model, you need to have a 2 in this term to get 2 times the Corning stiffness, basically, because you've got 2 tires generating lateral forces. Okay, so you've got a 2 in there, okay? And so we can rewrite these equations and these equations. Okay, so alpha F. Okay, so rearranging this equation, alpha F is going to be F divided by 2 C alpha F, which is there. Okay, and FYF we know equals this term or this term. It's up to you which one you use. In this case, I've used this term up here. Okay, so that's an equation to work out what the slip angle is. Okay. So we've got the lateral force being generated by the tires is 2 times the Corning stiffness at the front times by the slip angle at the front. Now, what we don't know often is what the slip angle is. Okay, and so this is a constant, so we can look this up. This we can work out from a bunch of the vehicle states. Okay, and so we can work out what the slip angle is by dividing this term by 2c alpha f. Okay, so that's here, and FYF equals this lot up here, d upon L mv squared upon R. Okay, so there's your 2 C alpha F, there's your d upon L mv squared upon R. Okay, so that's the equation for the front slip angle, and that's the equation for the back slip angle. So the same process. We divide FYR by 2 C alpha R. Okay, so there's our 2 C alpha R, and FYR is C upon L mv squared upon R. Okay. Like I said, if you work out what the front and rear masses are, then obviously you can use those equations as well for mv squared upon R. So the steer angle. So going back to the bicycle model, you can work out what the steer angle is. Okay. Well, the steer angle, we start with the Ackermann angle, which is L upon R. Okay. But then add on the front slip angle, and then you take away the rear slip angle. So from geometry, okay, we can work out the delta is L upon R plus alpha F minus alpha R. And that's the sort of steering angle determination when you've got a higher speed corner, when you've got slip angles on. analysis is asking what C alpha is. That's the cornering stiffness of the tyre. Okay, and that is very much dependent on the design of the tyre. Okay, C alpha. Okay, so like I said, delta is L upon R plus alpha F minus alpha R. Remember, so L upon R in meters, okay, if you take your wheelbase in meters divided by the radius in meters, this will give you a value in radians, okay? Whereas often these calculations will actually give you something in degrees. And clearly for this equation to be valid, they all need to be in the same units, okay? So often what we do is we multiply L upon R times by 180 over pi. Okay, sometimes you'll see that as 57.3 because that is 180 over pi. Okay, plus alpha F minus alpha R, and that will give you the value for the steer angle. Okay, so we can replace alpha F and alpha R with these equations here and end up with this lot. Okay, so clearly we've got an MO upon 2L in both of those terms. Okay. We've got a v squared upon r in both those terms, so that can come out this side. Notice we know what that is. Okay, there's our lateral acceleration, and then we've got determinant, which is to do with the front and rear slip angles. Again, for linear tyres. All good? Now we can look at this slightly differently. We can actually split this up into and make some substitutions. This term here, okay, is known as the understeer gradient, okay, and that is called Ku. So it's a gradient, some constant in terms of it's called the understeer gradient, and that's a function of the mass, the wheelbase, and the cornering stiffnesses of the car, okay. And obviously, if you've separated that term out, then this term we know that we've seen that already. That term there is the lateral acceleration in meters per second squared. Okay. So when you look at some of these things in the text, they might refer to accelerations in terms of g, in which case you've got some different terms up here. This will be the weight of the car, and you've got a g term down here, which gives you the lateral acceleration in terms of g. We're just doing it in meters per second squared because that is what we're used to. Okay. And so you can rewrite that equation for delta to be L upon R plus Ku times by AY. Okay, and that gives you the steer angle under these situations. So if you've worked out what the understeer gradient is, you know the lateral acceleration, you can work out what your steer angle is from those things as well. Okay. Now, when we're thinking about this, we can actually talk about some vehicle characteristics of the way the vehicle goes around the corner. Okay, and that depends upon the value of the understeer gradient. Okay. So we'll talk about three different states. We'll talk about neutral steering, okay, oversteer and understeer. And this is, like I said, depends upon the value for the understeer gradient, depends upon the front and rear rate distribution and the tyre characteristics. And like I said, Ku can be 0, positive or negative, okay, and those whether it's these values will determine the vehicle state, okay. So like I said, neutral steering, understeering, and oversteering. So the three different states we'll talk about. So with when the Ku is 0, okay, clearly what you end up with, if you think about this equation here, if Ku is 0, your steer angle is simply your Ackermann angle, okay? And so that means that you've got what's known as neutral steer, okay? On a constant radius turn, no change in the steer angle will be required as the speed is varied. So imagine you're going around in the car in a constant radius corner, because this is all steady state, okay, so we're not dealing with transients going on here. The vehicle's at a certain speed going around a constant radius corner, okay. As you increase the speed, the steer angle required will be the same, and that's L upon R, okay. That's for a car that handles with a neutral characteristic. Okay, as you increase the speed, the steer angle doesn't need to change. Okay, and that's simply L upon R. So Ku 0, that means your front slip angle and your rear slip angle are equivalent to each other. Okay, so you're still generating slip angles. It just happens that the front and the rear distribution is they're equal to each other. Okay, and your front and rear slip angles are going to be the same. Okay. Now, this is often why car makers and manufacturers sort of talk about this perfect weight distribution of 50-50, because if you've got the same tyres front and rear, okay, and 50-50 means that C and D are the same tyres front and rear, you end up with this zero characteristic, which gives you neutral handling, okay, which is obviously quite nice, because it means that irrespective of how fast you're going, the steer angle that's required will be the same irrespective of how quickly you're going. Okay, so that's quite a desirable characteristic. It's not always possible depending on the vehicle. Anyway, so we've got this zero understeer gradient. So the slip angles front and rear are the same thing. Okay, alpha F equals alpha R, and that means that the steer angle itself is simply L upon R. Now, if the understeer gradient is positive, I guess this is why it's called the understeer gradient. Okay, on a constant radius turn, the steer angle will have to increase as the speed increases. Okay, it is the vehicle that's understeering, not the driver. Okay, bear that in mind. Okay, so again, you're going around a corner of a constant radius. Okay, but as you increase the speed of your vehicle, you have to apply more steering lock to maintain that radius of the corner. Okay, the car is in a sense washing out the. Okay, so you apply more steering lock, generates more lateral force at the front, which hopefully will keep that radius of the corner the same. Okay, and that's the vehicle understeering. Okay, the vehicle response is under what is required by the driver. So the vehicle, like I said, is trying to wash out, trying to make the radius bigger, and so the driver has to apply more steering to get the vehicle to do what he wants it to do. Okay. It will increase linearly with lateral acceleration. Okay, which is obviously based upon the square of the speed. Okay, and that, like I said, that's your Ku times by A. So we go back to the equation. Okay, so if Ku is positive, okay, as your lateral acceleration goes up, if K is positive, lateral acceleration goes up, you end up with this value getting bigger as AY increases. So you have to apply more steering lock, because those two are constant, more steering lock to maintain that radius for the corner. Okay. So the front wheels are slipping sideways to a greater extent than the rear wheels. Okay, you've got a positive understeer gradient. Okay, that means that your front slip angle is bigger than your rear slip angle. Okay, which means that, like I said, as you increase the speed, you've got to apply more steering to maintain the radius of the corner. Okay, and this is the way most sort of modern road cars are set up, because it makes sense that if the vehicle's starting to slide, you apply more steering lock in the direction you want to go, and that will help you go around the corner. Okay. Whereas oversteer, which is what we'll talk about in a second, actually requires a bit of skill to balance that oversteer situation. So on an oversteer, that means that the understeer gradient is less than 0. Okay, and the idea with oversteer is to maintain the radius of the corner. You actually have to decrease the steering angle. Okay, which, like I said, is counterintuitive, and that's why most road cars aren't set up to oversteer. Naturally. Often you can obviously get a car into an oversteer situation, but yeah, like I said, to maintain the corner, you actually got to turn off the steering lock. Okay, the vehicle response is beyond what's required by the driver. Okay, so you've got to wind the steering lock to maintain the radius of the corner, and it will decrease linearly with lateral acceleration. Okay, the square of the speed. Okay. And that means that the rear wheels are slipping sideways to a greater extent than the front wheels. Okay, and so the Ku is less than 0. Your front slip angle is less than the rear slip angle, which means that as you increase the speed, you've got to wind the steering angle off to maintain the radius of the corner that we were talking about. Okay. If you want to think about it, neutral steer goes around the corner. Understeer, you crash nose first. Oversteer, you crash back end first. Okay. You want to try and stop those things. So you've got your various states. So down here we've got the speed is v. Okay, as we said, it increases with the square of the velocity. And so neutral steer. So down here, you've got neutral steer is L upon R, and so that's your steer angle, irrespective of how fast you're going around the corner. Okay, with a KU greater than 0, okay, you've got an understeering vehicle, okay, so that means as you increase the speed, you need to apply bigger steer angle to maintain the radius of the corner. Okay, so as you increase your speed, the steer angle is going to grow as you go faster and faster. Okay, and oversteer, like down here, okay, you can see that as you increase your speed, you have to take off the steering lock as you're going faster and faster. And that will work until you get to two certain speeds. So here we've got characteristic speed, okay, and the critical speed. Now for understeering car, you can have a characteristic speed, but you can't have a critical speed. And for an oversteering car, clearly you can't have a characteristic speed, but you can have a critical speed, okay? And these two things are certain states. So the characteristic speed is the speed at which you're going where the steering angle required is twice the Ackermann angle, okay? So up here, that's a certain speed, okay? That's called the characteristic speed. So when the steer angle required is twice times by the Ackermann angle. And with the oversteer situation, there's a critical speed, okay? And the critical speed is the steer angle required. Well, it's the speed at which the steer angle required to maintain that corner radius is actually 0, okay? So the car is going around the corner at a certain speed, and you get to a certain point with an oversteering car where you need actually 0 steer angle to maintain that radius of the corner, okay? The back is dipping wide enough such that the steer angle required to maintain that corner radius is 0, okay? Clearly, you can go beyond the critical speed, and that's where you get the situation where you've got to apply steer in the opposite direction, and that's your opposite lock type situation, which is where your drifting stuff comes in. If you want a car to oversteer, like for cameras or for drifting competitions or whatever, then you have to go beyond the critical speed, and you're applying steering lock in the opposite direction to maintain the corner radius, okay? But often those situations aren't particularly steady state, so some of the stuff is slightly different behaviours. But essentially, that's what's going on. Okay, so that's the situation. Now, clearly, like I said, this is 2 times L upon R. We can actually work out what the that speed is going to be. Okay, if we think about for an understeering vehicle, the characteristic speed is twice the speed at which the steering angle. Is the speed at which the steering angle is twice the Ackermann angle. So delta is going to be 2 times L upon R. Okay, and then that means that we've got L upon R. That means that this slot here must also equal L upon R. And in this term here, AY, there's clearly going to be a V term, so we can actually work it out. So this is going to be KU V squared upon R equals L upon R. Now there's your 57.3, because this term is in radians and this is often in degrees. Okay, so there's a 180 over pi equals V squared upon R times by KU. So you can rearrange that equation, solve for V, you get a square root. The characteristic speed is going to be 57.3 times by L divided by KU. That's different disappear. So irrespective of the radius of the corner, you can work out the characteristic speed of the car. And it's based purely on the wheelbase, okay, and the understeer gradient. Okay, so again, longer the wheelbase, the higher the characteristic speed is going to be in the vehicle. So that's the characteristic speed. Okay, yes, Thales, have you got a question?
Yeah, where did the 2 go on the equation?
Which 2? This one here. This 2 here. Okay.
Yeah.
Well, basically, for this to be true, then KU times by AY must equal L upon R. Yeah. If this is 2L upon R, yeah, then we've got L upon R here plus L upon R. Okay, so KUAY must equal, that's KUAY must equal L upon R. Does that make sense?
I didn't quite understand.
Okay, so we've got an equation here. Delta is going to be, like I said, delta needs to be 2 times L upon R up here. Okay, and so for this, and that must equal, this is the equation for steer angles. Okay, so it's L upon R plus KUAY. Okay, so delta, we know what delta is because it's twice the steer angle. Okay, but what we want to work out is the speed at which this point happens. Yeah.
Yeah.
Yeah. So that's 2 times L upon R, and that we know that delta also equals L upon R plus KUAY, which is what we worked out earlier. Okay, so for this equation to be true, this term, KUAY, must equal L upon R. 2 times L upon R, yeah?
Okay.
Does that make
Yeah.
sense?
Yeah.
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 So that's
Makes
where
sense.
this comes from down here. So we've got KU times by AY, okay, which is this term here, must equal L upon R, okay? And like I said, the 57.3 is there but to convert this term into degrees, because often this one is determined in degrees, okay? So that's now matching that up. And then this equation is simply rearranging to solve for V, which gives us the characteristic speed V, which is
Yeah.
7.3 L upon KU. Is that clear?
Thank you.
Okay, great, thank you. Now, for the critical speed for oversteering a vehicle, this slide should say critical speed up here, not critical speed, so I should change that. Critical speed. For oversteering a vehicle, the critical speed is when the speed at which the steering wheel is 0. So in this case, delta equals 0, which equals L upon R plus KUAY. So clearly this term has to equal minus L upon R. Yeah, that plus this must equal 0. So this term must equal minus L upon R. Okay, so that KUAY equals minus 57.3 L upon R. Okay, so your critical speed is going to be minus 57.3 L over KU. Now you're thinking, hold on a second, I'm taking the square root here of a minus value, but clearly for this situation, KU is also negative. Okay, KU is less than 0, so actually you've got a minus term over a minus term, so the whole thing becomes positive, and that will give you a critical speed. Okay, so it's very similar to the other one. Characteristic speed was where has it gone? Characteristic speed was 57.3 L over KU, and the critical speed is simply the same thing, but obviously you've got minus 57.3 L over KU. Okay. So that's the end of this lecture. Okay, like I said, there are 2 in-class questions. I can go through, like I said, I could either, like I said, I can do a video of them. So with this question, we've got a wheelbase of a certain value. It's driving around the corner of 250 meter radius at 60 miles an hour. Okay, you've got a car weight of 1780 kilograms. Okay, so the car mass of 17 mass of 1784 kilograms, and the weight is distributed front to rear in a ratio of 4 to 3. Okay. And then we've got corner stiffness values for the following loads are given below. And the question asks what's the front rear slip angles, what's the lateral acceleration, steer angles, understeer gradients, cooling state, and the characteristic speed. And like I said, what I will do is I will produce a video of the solution to this question. Excuse me, my children are interrupting me. Right. So yeah. So like I said, you've got to work out what those values are. And then the question 3 is the same question basically, but this time we've got 2 to 3 as the weight distribution, okay? And this time you've got to find the critical speed because the cornering state for this one will actually be oversteer. But the idea is that you show how you've worked out those things out. But like I said, I think the easiest way to do this is possibly for you to have a go in your own time. But I shall put up a video of the solutions when they're that you can look at after the lecture. Okay, they will be done very shortly. Next week we should be covering margins, okay, and stability, and we'll do it in the same way that we've done this lecture with using Blackboard Collaborate. Hope you're all well. Hope you stay safe. Don't go out. You know what the government's advising. Just keep yourself from a safe distance and stuff. Okay, thank you very much. Cheers.